Hello, my name is Mahmoud Nabil, currently a PhD student at the Autonomous University of Yucatan. The content of this poster is part of my master's degree thesis, in which the objective was to recover zinc oxide nanoparticles from a commercial product, to characterize the extracted particles, and to see whether they could be recycled and used in other applications, for instance, as electron transport layer in solar cells.
So it shows a commercial skincare product which is called La Pomada de la Campana. It contains zinc oxide along with organic materials. And then we performed the following procedure. A potassium hydroxide solution of 0.3 moles per liter was prepared, and 30 grams of the commercial product were put on a hot stirrer plate at 60 degrees to melt. After melting down completely, the KOH solution was added by slow dripping, and the mixture was stirred for 30 minutes, and then it was left to settle down for 24 hours. By then, three layers were clearly formed in the beaker: a top layer containing the organic materials found in the commercial product, a layer of zinc oxide particles precipitated at the bottom, and a colloid between them which contained the solution of KOH with suspended zinc oxide nanoparticles. The organic top layer was separated from the beaker, while the colloid and the precipitate were stirred again overnight. Then, from the mixture of colloid and precipitate, we deposited thin films of zinc oxide on clean glass substrates using spin coating technique at 3000 rounds per minute for 15 seconds. The films then were annealed at 550 degrees for 1 hour.
We used Z-sizer analysis to determine the size range of the extracted zinc oxide nanoparticles. Directly after the extraction process, 92.4% of the zinc oxide nanoparticles were in the range of 45 nanometers to 190 nanometers. And after magnetic stirring overnight, 97.5% of the amount of zinc oxide nanoparticles were in the range of 35 nanometers to 100 nanometers.
The scanning electron microscope images for the zinc oxide thin films showed the presence of crystals of different sizes arranged in a mesoporous form. The smaller particles were those suspended in the colloid and shown in the Z-sizer analysis results, while the larger particles were of the precipitate, with estimated particle size of up to 450 nanometers. We performed an energy dispersive X-ray spectroscopy analysis that identified only the peaks of oxygen and zinc, which indicates the purity of the extracted zinc oxide. We performed an X-ray diffraction analysis where the peaks of the sample coincided with the standard diffraction pattern of zinc oxide in its hexagonal word-side shape, with no evidence of remnant materials or impurities. Based on the data from the X-ray diffraction analysis, we applied the Scherrer's formula to calculate the average crystalline size, which was found to be 43.25 nanometers. We also calculated the average induced strain, the dislocation density, the lattice parameters of the crystal structure, and the crystal volume, where all the values were within the range of other reported values of synthesized zinc oxide. The lattice parameters showed a slight expansion in the zinc oxide crystals that results in an increase of 0.7% compared to the standard zinc oxide crystal volume. We measured the absorbance spectrum of the deposited zinc oxide thin films and estimated the band gap to be approximately 3.8 electron volts, which is higher than the standard band gap value of zinc oxide. The higher optical band gap value could be attributed to the previous treatments performed during the fabrication process of the commercial product in order to optimize its use for dermatological applications. So through the developed chemical process, we extracted the zinc oxide material from the commercial product La Pomada de la Campana in both colloidal and precipitate forms, obtaining a range of particle size between 35 nanometers and 100 nanometers for the colloid and below 500 nanometers for the precipitate. By controlling the deposition parameters, we obtained zinc oxide thin films using the spin coating deposition technique. This study opens the door to the recycling of oxide nanoparticles, an area that has little research to date but great importance and potential for the future. The obtained zinc oxide thin films have physical and optical properties that are suitable for their application in third-generation solar cells.